Welcome to Calculus. Today we will investigate how to find volumes of revolution about the x-axis, and we'll look specifically at the disk method. We'll take a look at two examples. Our first example involves the function y equals negative x squared plus 4, and we're considering that graph between that and the x-axis, which is the line y equals 0. I want to start off by graphing that function. So I know for this negative x squared plus 4, that's a quadratic that has been reflected over the x-axis. So I see that values for this function are really going to be from the x-axis up, since I know that's the region that I want to revolve around the x-axis. So I'm just going to consider where this function would equal 0, and that's got to be at 2 or negative 2. So I definitely have the point negative 2, 0. Negative 2 squared is 4. Negative 4 plus 4 is 0. Then I also have a point up above here at 0 of 4. If I plug 0 in the equation, 0 squared is 0. Negative 0 plus 4 is 4. And then it's a very symmetric graph, so it's also got a point here at 2, 0. And just kind of using the quadratic pattern, I can sketch this curve. So I want to revolve this region between that curve and the x-axis around the x-axis. So I'm just going to highlight there. Revolving this around the x-axis is going to create our solid. So what I'd like to do is set that up as an integral. So what the case that we need to make about how to find the volume of such a solid that I've revolved around the x-axis is that it's really going to follow the path of a circle. In fact, every point on that revolution is going to be in a circular path. So the rationale behind the setup is that geometrically. So our volume is going to equal really the area of a circle that's defined as having its radius of the function. So just in general terms, it's going to be pi r squared. The way we're going to treat the radius is the integral from a to b of my function. And that whole expression is really my radius. And so what I'm thinking is that I also need to square that, because the formula for a circle's area is going to be pi r squared. And then we'll wrap that up with dx. So that's in general how we want to integrate. Let's set it up for this specific example. So the volume of this solid is going to be equal to pi times the integral from the left, negative 2, because we're revolving around the x-axis, to the right, positive 2. And my function is going to be negative x squared plus 4. That's the quadratic that we graphed, squared dx. So now once I've got it set up, I just want to integrate with my usual strategies. So I'm going to just record that pi as a constant coefficient. And then what I'd like to do is square this quadratic out. So negative x squared times itself is going to be positive x to the 4th. And then I've got the outer and inner terms from that squaring. So the one multiplication is going to be negative x squared times 4. So that's negative 4x squared, but I've got two of them. So that's going to be negative 8x squared. And then lastly, my last terms in the foiling, 4 times 4 is going to give me 16. So now I'm ready to actually integrate. At that point, I'm going to record again the pi. It's really a steady stay-in-place coefficient. But now I'm going to integrate my 4th degree polynomial there. So it's going to be 1/5 times x to the power of 5. That's coming from the integration of x to the 4th. Minus 8 times 1/3 x cubed plus 16x. And I want to evaluate according to fundamental theorem of calculus from negative 2 to positive 2. So I do want to apply fundamental theorem of calculus to evaluate this statement. So it's going to be pi times, I'm going to plug in 2 for x here, and we always start with that upper limit. So it's going to be 2 cubed, I'm sorry, 2 to the 5th, which is 32 times a fifth. So that's 32 over 5. Then plugging in a positive 2 for my x and x cubed, that's going to give me 2 cubed, which is 8, times the other 8 is 64 over 3. So minus 64 over 3 plus 16 times 2, which is going to be 32. So that's from the substitution of positive 2. Now we'll substitute in negative 2. And I see because all my powers are odd, 5, 3, and an implied power of 1, the negative sign on my negative 2 is going to be preserved. So basically, it's the same values for my first substitution, but just opposite signs. So negative 32 over 5 plus 64 over 3 minus 32. Now, you might be tempted to think that'll all cancel out, but it's not going to, because I've got a negative that's really programmed in there by fundamental theorem of calculus that when I distribute to the 3 terms in that second group, they're all going to switch signs, which is going to make them identical to the terms in the first group. So one way I could write that is as 2 pi times 32 over 5 minus 64 over 3 plus 32. So now I actually want to combine those fractions. I see I've got least common denominator of 15. So the way that I'm going to scale that is multiplying 32 by 3. That's 96 over 15. And then for 64 over 3, I need to multiply by 5. So 64 times 5 is 320. Also now over 15. And then 32, I need to multiply by 15. So that's a large value, 480 over 15. And that gives me occasion to add those 3 fractions. So 96 minus 320 plus 480 is going to give us the fraction, let's see here, 256 over 15. And then multiplying through my 2 pi, I'm going to get double 256, so that's 512 over 15 pi. And that's an exact answer. If we were to multiply that out and get an approximate decimal, we'd have 107.233 units cubed, cubic units. So I'll box both the exact answer and the decimal approximation there. So our first example is a nice algebraic function. It's a quadratic. Let's take a look at a trigonometric function that we could revolve around the x-axis. So our second example is the function y equals cosecant of x. And we're going to consider this graph, but we're going to really constrict it. I want to look between that graph and the x-axis, so y equals 0. But I'm going to really limit my domain. So it's only going to be from pi over 2 to 3 pi over 4. So it's a very small slice of that graph. But let's start graphing that one just so we can see cosecant on our plane. So recall cosecant is the inverse, or the reciprocal rather, of sine. It's equivalent to 1 divided by sine of x. So basically, if I find the value for sine and divide it under 1 and reduce, I'll get values for cosecant. So I always start at the x-axis for that, or I'm sorry, the y-axis. That's where x equals 0. So sine at 0 is 0. 1 divided by 0 is undefined. So that's where we got our vertical asymptote for cosecant. So I'll move to the right from there. So I see I've got pi over 2, but let me consider also pi over 4. So at pi over 4, sine has the value of square root of 2 over 2. That's that isosceles right triangle at the 45 degrees. So if I were to flip over and divide 1 divided by square root of 2 over 2, that's all going to reduce to square root of 2, which has the value of about 1.414. So I'm going to graph that there. At pi over 2, sine has a value of 1. So 1 divided by 1 is 1. And then again at 3 pi over 4, which is our upper limit, coincidentally, that's another 45. But now the x value is negative, but that doesn't really affect sine. The sine value is positive because the y value at 3 pi over 4 is positive. So that's also going to have the value of square root of 2. Then at pi, sine has the value of 0 again. 1 over 0 is undefined. And that's where we get another vertical asymptote. And we can see one of these full periods of the cosecant function kind of looks like one of our, I don't know, quartic, maybe degree 6 polynomial functions. Recall though that cosecant does keep going on either side. If I were to quickly sketch something here in quadrants 2 and 3, what would happen is it would have the same shape, but it would be reflected across the x-axis. So something like this graph here. And then as you're familiar with cosecant, you know that that pattern continues indefinitely to the left and the right. So that's enough for us in terms of a graph. What we want to rotate about the x-axis is this region. So from pi over 2 to 3 pi over 4, and it's the region bounded by the curve above and the x-axis below. So that's the area that I want to revolve about the x-axis to create a solid of revolution. So to do that, we're going to use the same setup as we did on our first example. So just to remind, that's volume equals pi. Again, because we're really thinking pi r squared, we're considering that these are radii that we're revolving around the x-axis. And again, the radius is determined by the function. So we're going to integrate from a to b of f of x squared because it's pi r squared dx. So we'll set up for our specific example here. Our volume is going to be equal to pi times the integration from pi over 2 to 3 pi over 4 of this function cosecant of x squared dx. So again, that's my setup. And I could rewrite that as just pi integration pi over 2 to 3 pi over 4. This is such a small change, I almost hesitate to write it, except that it kind of gives us some insight into the antiderivative. So I'm just moving that square so that it looks like cosecant squared. Well, when I go to integrate, recall that the antiderivative of cosecant squared is going to be negative cotangent. It's got to be negative cotangent because the derivative of cotangent is negative cosecant squared of x dx. So I've got to include a negative on the antiderivative to cancel the negative that I would see normally in the derivative. Well, that helps us to integrate here. So this is now going to be equal to pi. So again, you see that pi, it's a very steady coefficient there, doesn't change. And our integration is going to be negative cotangent of x, evaluated from pi over 2 to 3 pi over 4. So we're ready to plug in and evaluate according to fundamental theorem of calculus. So I'm going to put negative cotangent of 3 pi over 4 minus negative cotangent of pi over 2. So even though this is in a way, a more complicated function, it's a lot smaller. I've only got one input, so the evaluation is a little simpler than our 3-term polynomial in the first example. So let's just calculate these values. So cotangent, one way to think about that is that it's 1 over tangent. So tangent at 3 pi over 4 is going to be negative 1. The reciprocal of negative 1 is negative 1. So what we've got for that first one is negative from this negative out front of negative 1. We'll also write our double negative there in front of the second cotangent. Cotangent of pi over 2. So tangent at pi over 2 is undefined. It's 1 over 0, sine over cosine. So if I flipped that over, that's 0 over 1, which is just 0. So this really reduces down to just positive 1 plus 0, which is just 1. 1 times pi is just pi, which has the value of about 3.14. We can get a few more decimals for pi. Let's see if it'll give it to us here. So 3.142. And again, I would put cubic units because we've created a solid of rotation. Thanks for joining for these two examples of calculating volume of a solid of revolution about the x-axis. See you soon.